Welcome to the talk Evaluating Explanation Methods for Deep Learning in Computer Security. My name is Alexander Warnecke, and this is joint work with my colleagues Daniel Ab and Konrad Rieck from the Institute of System Security at the Technical University of Braunschweig and Christian Bresnegger from Karlsruhe Institute of Technology. This presentation deals with neural networks, which are increasingly used for computer security applications like Android malware detection or finding vulnerabilities in source code. These networks oftentimes show great performance, but at the same time their decisions are opaque for the practitioner. This means you cannot directly understand why a neural network makes a prediction the way it does. In recent years, a remedy occurred by so-called feature attribution methods. These methods assign relevance values to features indicating their importance for the classification. In this example on the left side, we can see that the head of this bird was important for a deep neural network to classify the image correctly as a kakadu. However, a variety of feature attribution methods exist, and most of them are designed for images. Until now, it is an open question which of these methods are suited for the computer security domain and how one can compare explanation methods at all. We are going to tackle these questions in the upcoming talk. We make the following contributions. We define 6 criteria for comparing explanation methods. These criteria contain general criteria, but also criteria suited only for the computer security domain. In a study on 4 datasets with different networks, including multilayer perceptrons, convolutional neural networks, and recurrent neural network, we evaluate 6 different explanation methods and derive general recommendations for selection of explanation methods in computer security problems. Finally, we qualitatively evaluate explanations on all datasets and find out what these models have actually learned for the underlying task and if it is useful in practice. Now I will guide you quickly through our criteria. The first one is descriptive accuracy and measures the impact of important features on the classification. Generally, a good explanation method assigns high relevance values only to features with big impact on the classification. To this end, we remove the k most important features from a sample and classify it again to see how the classification changes. Next up, we have descriptive sparsity, which measures how sparse explanations are. In practice, you would like to have sparse explanations where only few features are important so that you can inspect these features easily as a human expert. To this end, we compute histograms of relevance values to see how many of them receive a relevance value close to 0 and can thus be ignored by the human expert. Completeness deals with the problem of degenerated explanations, which occur for certain explanation methods. A degenerated explanation makes no sense and can, for example, be an explanation that assigns each feature the relevance value of 0, which makes no sense and doesn't help an expert in practice. We measure which methods are affected and the extent of failure. Stability deals with the problem of non-deterministic outcome of explanation methods. We check the deviation by repeatedly creating explanations and seeing how different they are. Robustness deals with attacks on explainable learning methods which emerged recently. These attacks add small perturbations to an input that do not change the prediction but can drastically change the explanation, which poses a major threat for these systems in practice. We check which methods are affected and how large the attack surface is. Finally, we measure the efficiency of explanation methods, which is the runtime they need to explain one sample. This is important because in general you have large datasets and want to compute a large amount of explanations in a reasonable amount of time. Finally, we compute a metric for each criteria and average them over all datasets for each explanation method. Ideally, we would like to have an explanation method that excels in all criteria. However, we find that only few methods achieve that and even explanations can differ significantly depending on the network, architecture, and dataset at hand. In general, we can recommend the layer-wise relevance propagation and integrated gradients method, which are well suited for problems in computer security. In a general view, we can say that white box methods, which have access to the parameters of the underlying model, outperform black box methods, which have only access to the outputs of the model. We also find that each method can be attacked by an adversary, which poses a general problem in the research field. Now I would like to show you two example explanations to see how they look like in practice and what we can learn about models using these explanations. The first one comes from the Warnecke network, which is a recurrent neural network used to detect vulnerabilities in source code. On the left side, we see a code snippet where the memmove call in line 7 causes a buffer overflow because it copies data from a buffer of size 100 into a buffer of size 50. On the right hand side, we see which tokens are important for Warnecke to detect this code snippet correctly as containing a vulnerability. Investigating these important tokens, we find that a lot of artifacts are highlighted in the snippet. For example, semicolons are important, although almost every line of code in C ends with a semicolon. Likewise, we see equal signs, brackets, or commas highlighted, which also have small influence on vulnerabilities from a human point of view. We therefore judge that Warnecke simply overfitted the entire dataset and did not learn what a vulnerability is and how one can predict them. We also see that even though we have explanation, it's still hard to understand what's going on in the model. So there seems to be a semantic gap for this model that doesn't allow us to fully understand the explanation we get. The second example is from the deep Android malware detection paper, where a convolutional neural network is used to detect malicious Android apps by using decompiled bytecode sequences as input. An example for such a sequence can be seen on the right hand side, and using the explanations in this case we find that they are really helpful to analyze the applications. For example, these decompiled bytecode sequences can easily contain hundreds of thousands of codes which are impossible to inspect for a human. With the explanation methods, however, few features but important features are pointed out, and an analyst can jump to the corresponding point in the program. In this example, we see a part of the onReceive method of the Goldgreen family malware. The most important token corresponds to the point in the program where an incoming SMS and phone call is intercepted and data is sent to a server. Interestingly, the same sequence is highlighted in each sample of the family, showing that the underlying model has really learned what malware is and what makes an application malicious. Since it is always hard to pick certain samples for qualitative analysis, we decided to publish a large portion of explanations we created for our paper online on our project website explain-mlsec.org. There, you can choose certain explanation methods you would like to compare and see side by side for each feature which are the most important ones according to each method. You can also sort the features alphabetically to see directly for each feature the relevance value each method assigns to it. This brings me to the end of my presentation. I would like to thank you very much for your attention, and I'm really looking forward to answering any questions that occurred in the upcoming question session. Thank you.